Advanced Math Lesson 51, we're talking about common and natural logarithms. Now, a couple of things that we're going to set some basis up for here to begin with, and that is that there's some understood values when we're talking about logarithms and natural logarithms. And the first thing is that a lot of times in math, rather than write a common thing, we don't write it at all. We just understand that it's there. One of these would be like the understood 1 in front of this x. If I just wrote x, we understand there's an understood 1 in front of it. Or we could really say there's an understood 1 underneath it. Or a better example would be when we write the root of x. The root of x is the same as, well, there's a 2, but we don't write that 2 in there unless we explicitly need to tell someone there's a 2, because normally there wouldn't be, but there always is. So it was just a common thing that we don't write that 2. We just drop the 2, and we only put it in there if there's something different. A couple of natural things, natural logarithms that occur, or logarithms in base 10, are so common that we're going to drop them. So instead of saying, in the past we would have written log 10 42 like this, we're going to just say log 42. That's understanding there's an understood value of 10 hiding right here that we don't need to put in there for logarithms. Now, that happens in real life so much because we work in base 10. We count in base 10. We think in base 10. It makes sense to us to work in base 10. Another one that comes up a lot is base e. And I put the value of e. I want you to think of a lot like you would pi, where it's an irrational number. It does not have an ending to it, so we assign a letter value to it. Where that happens quite often is in calculus or in finance, when I'm finding an interest rate that's recalculated infinitely. That e comes in handy. And so that value of e is something that naturally occurs, and that's called the natural logarithm. Instead of writing log e 42, the way that we can differentiate that is saying ln 42. Now, it's pronounced like I'm going to mow my lawn, L-A-W-N. However, it's abbreviated just L-N. Okay. Now, when I'm working with these, I'm going to see ln 42 means the natural logarithm of 42. And if I just put log 42, I immediately know that that's going to be the same as log base 10 of 42. Now, we've worked with logarithms and switching their order around, but we've not gotten into where they're actually valuable for real life. And what we're going to hear is, if we look at example 51.1, and we're going to set this up so that we can actually use them. In physics, we would use them for calculating the power of the wattage when we're talking about sound power, and we're converting that into decibels. Or the Richter scale would be another logarithm type problem, where we say the difference between a 5 and a 6 on a Richter scale. We're counting the exponents. We're not counting what the actual magnitude is. It's a power of it. And that's where this is going to come in handy for us. And the question asks us to write 2.4 as a power with a base 10 and a base e. So we're going to write 2.4 as a power. Now, this is really simple with your calculator, and I have my calculator here. Well, I did. I will find my calculator momentarily. This is a really simple problem on the calculator. If you just simply hit log 2.4 and then hit enter, it's going to give me a value of 0.38 and then continue. That means that 10 raised to the power of 0.38 will equal 2.4. Now, I can't seem to find my calculator at the moment, but that's all right. If you will go ahead and, here it is. If you will go ahead and do that on your calculator, you will see that I put in on my calculator here log 2.4. And when I did so, I got a 0.3802112. This is the first value that I went ahead and entered ahead of time. That's what this, when I put in log 2.4, I get. And what that's telling me is if I took the value of 10 and raised it to a 0.38 power, that when I did so, I would get a value of 2.4. Now, you realize that if you want to think of this logically, 10 raised to the 1 power would be what? 10 times is 10. But if I raise it to the 0 power, it's 1. So it's between the values of 0 and 1. Well, 0.38 is what 2.4 would represent. And this allows us to convert this format. If I do the same thing with the ln, I'm going to hit ln 2.4, and I get this value here. And you can see that's my second value on my calculator. And that ln value is going to be 8.87, 5468, so on. That's what e raised to the 0.88. Now, if I remember right, e is just going to be 2.17 continually here. This is a really nasty number to try to work with. But what I'm saying is this number here raised to the power of 0.88 is 2.4. So it's not quite raised to a whole power of 1. It's a little less than that, and that's where we get this. Okay, so 2.4 raised to the 0.88 power is going to give me that value, 0.875, so on. Now, look at 51.2. Find the log of 2.4 and the ln of 2.4. Well, we just did that. I hit on my calculator log 2.4, and that's going to give me a value of 0.38. I hit ln 2.4, and I get 0.88. Okay, so I have 0.38 and 0.88. If you notice here, I have a log and a ln button right there on the calculator for me. Notice that the second key is 10 to the x because the log deals with the base 10. And when I have a second key for ln, it's e to the x. That's important to recognize there because that's the inverse function, right? It's the opposite function of what it is, and that happens a lot on the calculator. So let's look at the next example here. 51.3 says find the write the power of 10. 2.4 is a power of 10, or 24,000. I'm sorry, is a power of 10. 24,000 is a power of 10. Well, it's not an even one. If it was even, if I did that, I would say, well, if I wrote 10 as a power to 1, that's 10. 2 is 100. 3 is 1,000. 4, and you understand what we're doing is just adding a 0 because we're saying how many times 10 is being multiplied by that. Well, we know it's between the 4th and 5th power because I've got 1, 2, 3, 4 decimals, right? The 4 would give it would work out with 1 and all those zeros. And if I went to the 5th one, it would work out with a 1 in this place here to the left of that 2 with all zeros after the 1. So it's between those two. Well, it does work out. If I hit log 24,000 on the calculator, it gives me 4.38. That means 10 raised to the 4.38 power is 24,000. Now, a couple of things I'm going to point out the book glosses over just a little bit. That is, these are very, very specific numbers. Meaning, if I wanted to go back and forth between those, I would need to keep up with every one of those decimal places that the calculator gives me. And even still, I'm going to have to round a little bit. So I realize that we're doing this, it's just an exercise because when I'm doing it, I'm rounding. And if I went back and said 10 raised to the 4.38 power, I'm not going to equal exactly 24,000. I would have to round with significant digits to get back to 24,000. 51.4 says find the write it as a natural log. So I hit ln of 24,000. This should be an easy lesson for you because we are using the calculator and we're just following these same steps over and over to get us a value. And so when I hit ln of 24,000, I get 10.08. I'm going to round that to 10.09. And so I have e raised to the 10.09 power is going to give me 24,000. Obviously, this is a bigger number than this one because this one has a bigger base 10, base e. So the base is over 3 times that, right? And that's where that number comes from, which is roughly represented here too. So these numbers all start to make sense. Hopefully this gives you a little better understanding of what logarithms are and why they're so important, and also introduces ln with that, and that being base e.